So a second example of being able to find a vector projection of u onto v, this time in 3 dimensions. So we have two vectors. U is 2i plus j plus 2k, and v is 3j plus 4k. Let's recall the formula for projection. So the projection of u onto v is going to be equal to u dot v over magnitude v squared times v. All right. And so let's just find u dot v first, then we can find magnitude of v and throw it into the formula. We also have to find the vector component that's going to be orthogonal to the projection. All right, so u dot v is going to be equal to 2 times 0, because notice that there's no I component in v, plus 1 times 3, plus 2 times 4, and that's going to be 11. Secondly, we compute magnitude v squared, which is going to be the square root of 0 square plus 3 square plus 4 square square, and that's just going to work out to be 25. All right. And so now the projection of u onto v is going to be equal to 11/25 times whatever v was, because remember it's parallel to v, 0, 3, 4. All right, we could leave it like that, or we could write it as 0, comma 33/25, comma 44/25. And so the other thing that we need is we need the vector projection, or the component that's going to be orthogonal. All right, so remember, to find W2 is going to be equal to u minus W1. Remember, W1 is just the projection of u onto v. So that's going to be equal to 0, 33/25, 44/25, minus w, or excuse me, I put that backwards. So it's going to be u, sorry about that, which was 212. And we're going to subtract 0, 33/25, and 44/25. All right, and we'll just throw that in our calculators just to make it pretty easy. All right, so that's going to be 2, and then -8/25, and then 6/25. As we did in the previous example, if you wanted to graph that just to verify, then you could see that this should be orthogonal to v. Okay, so again, W2 is that orthogonal projector to v, and the projection should be parallel to v. All right, if it's not, then go back and check again. Right. So just two very basic applications of being able to use a projection with respect to work. So a 4,800 or 48,000 pound truck is parked on an 8 or a 10-foot slope. Assume that only gravity is the force acting upon the truck. Find the force necessary to keep it still. So essentially what we're going to do is we're just going to project that vector onto the flat plane. Okay, so essentially what we have is we have a vector here, and we're just going to try to project it right here. And that's really easy, because we know that if we just take 48,000, which is going to be the amount of work, or I guess the force necessary, okay, so that's the force pulling on it, and we just take that force in the y direction, and remember the sine function represents the y direction. Okay, we could just literally put it in like that, and that's going to give us our projection. Okay, now I'm going to punch this in the calculator. Make sure you're in degree mode. And I wind up with 8335.11. And that's in pounds. Okay, so that would be the force necessary, which makes sense because it should take a lot of force compared to 48,000 because it's only a 10-degree incline. As that incline becomes steeper, then this number, 8,335, should become bigger. All right. A second example. So we have a toy wagon. It's pulled exerting 25-pound force on a handle that creates a 20-degree angle, and then find the work necessary to be able to pull the wagon 50 feet. So once again, what we're going to do is we are going to use a sine function to be able to project this, okay? Or in this case, we just want to make sure that this is being pulled in the x direction. All right, so we're going to take 25, which is the force, times 50, which is going to be the distance, right? And then since this time we want to pull it in the x direction, a horizontal direction, we're going to say this time cos of 20 degrees. All right? So remember in this diagram up here, the force was in the y direction, so we wanted to counter that. This time the force is getting pulled across, so we need a cosine to be able to work that nicely. Okay, so again, punch that into our calculator. And I get 1,174.62. And since we're finding the work necessary this time, not the force, this time it's going to be foot-pounds. So be careful. When we talk about a force, that's usually like a gravity. Okay, so that would be the weight. In this case, because we're trying to find the work, we have to use force times distance, and then we have to use the projection to put it into the x component. Okay, so hopefully this gives you an idea of how to apply the projection, and then also a 3D example as to how to work with this. So in the next video, we're going to start working with the idea of the cross product of two vectors.